this notation is defined as log with the base of e. You remember e we mentioned the last time. You also did a question about e on your assignment, right? This notation means nothing but a log with the base of e. We say this notation natural log. Okay. Natural log. When you say the function here we say natural log of x. Natural log of x. Okay, now we talk about we try to answer 4 questions. Okay, how the function is defined, how to evaluate the function, and then how to get the domain of the function, right? How to get the graph of the function and the range of the function. We need to answer 4 questions to understand the function. Now we concentrate on how to evaluate the function first. Okay. The value of the function at 1, we'll go over the list. The value of the function at 1, we are trying to compute natural log of 1. And by the way, the convention is that for this function you do not need to use brackets. It's okay to use brackets, of course. Okay, but it's not necessary to use brackets. So no y. So it's just convention. So everybody is doing that. So now let's say so natural log of 1. So this means the value of the function natural log at the number 1. Okay. I think you did a few questions about the log on your assignment. Okay. Now let's recall how we get natural log of 1. For natural log of 1, we compute natural log of 1. It means natural log of it means the log to the base e of 1, right? And then you think e to what power is equal to 1, or you remember an important point. Okay. So anybody want to tell me the value, please? E to what power is equal to 1? E is 2.7 something. We mentioned that last time, right? So natural log of 1. So please, anybody want to? 0. So 0 is right. Okay. E to the power of 0 is equal to 1. That's why natural log of 1 is equal to 0. And then we go over the list. Actually, because the base is a little weird number, I cannot ask you to evaluate too many values. We just go over the list. We do not do too many. Okay. Now let's say the value of the function at e. The value of the function at e. We think which e to what power is equal to e, right? As I told you last time, you look at the equation here. You think e to what power is equal to e? I believe you see natural log of e is equal to 1. Okay, cool. And then the value of the function at, now let's say e squared. By that we mean we are trying to compute natural log of e squared. You use the same thing as I told you, the same trick as I told you before. I believe this value is 2. Okay. And then the value of the function at e to the power of 1/2. Maybe you could also write square root of e, the same thing. Okay. So we're trying to compute the natural log of e to the power of 1/2. So which is 1/2, right? I will ask you two additional values. So maybe the value of the function at 0. So we're trying to get natural log of 0. The question is equivalent to you think, okay, on scratch paper, you think e to what power is equal to 0? E to what power is equal to 0? It's undefined. E to no power is equal to 0. E to every power, e to the power of any number is equal to e to the power of any number is equal to a positive number, right? So e to no power is equal to 0. So this one is undefined. Okay. one more. The value of the function at negative 10, maybe. For this one, we are trying to compute natural log of negative 10. In this context, negative sign, the sign negative sign is essential. Okay. If you take courses with me for a little longer, you will know I'm looking for proper notations. If you use wrong notations, you could confuse yourself. Okay. Again, I'm trying to say the negative sign here is essential. Otherwise, the notation does not make sense. Okay. This one is undefined as well. Again, e to whatever power is equal to a positive number. Okay. E to no power is negative. So this one is undefined. Okay. So we have answered the question, the first part of the question, how to evaluate the function. Okay. The second part of the question, we're going to see how at what x values the function is defined. By that we mean we're trying to get the domain of the function. Again, to get the domain, you get all the qualified inputs. Okay. Or you think at what x values the function is defined. The function is defined at 1. It's possible to evaluate the function at 1, right? Function is defined at e. Actually, the function is defined at any positive number. The function is undefined at 0. The function is undefined at negative 10, represented by these two numbers. You can imagine the function is only defined at positive numbers. Okay. Now we're trying to get the domain of the function. The domain of the function is the set of all the positive numbers. Now recall the interval notation. Yeah, that's right. From 0 to infinity. Round brackets on this side. Use that to mean 0 is not included in the domain. Okay. The open interval. The full name is open interval from 0 to infinity. The meaning is the set of all positive numbers. Okay. And then to get the graph, you just recall one thing. Each value of the function determines a point on the graph. In the domain, you have many points. By that we mean you have many possible inputs. Okay. And the many inputs will determine many points. Many points will form a curve. That curve is called the graph of the function. I will show you the computer sketch right now. That is the computer sketch of natural log function. You see, in here I wrote natural log of x. This is the graph of natural log of x. Okay. In particular, so because the base is e, you probably in high school you learned natural log of function and e to the power of x are reverse functions of each other. In this case, actually natural log of function is the reverse function of e to the power of x. You do not have to see that way. But I want you to look at this point. Now listen to me carefully. I'm going to say one thing. Okay? The slope of the tangent line to the graph of natural log at this point, to the graph of natural log of x at this point, at the point with x coordinate of 1 and y coordinate of 0, the slope of the tangent line is equal to 1. So maybe the same as last time, I can draw you the tangent line. I think the tangent line has the equation x minus 1, y equals x minus 1. And by the way, on decimals, the input, you do not have to write y in here. Okay. But the point I'm trying to say is, I want to repeat, okay, it's kind of important too. And the slope of the tangent line to the graph of natural log of x at the point 1, 0 the slope is equal to 1. Okay. For this function, I was just trying to say the graph. Okay. So the graph, I showed you the graph as shown. Lastly, the range. In most cases, using the graph of the function, you can see the range. Okay. I believe you can see the range as the set of all the real numbers. Now I'm going to write down the range. The range is the collection of all the real numbers, the set of all the real numbers. Using the interval notation, we use a notation like that to denote the set of all the real numbers. Okay, so natural log of function. Okay. Again, e to the power of x is probably the most important exponential function, and likewise, natural log of x is the most important log function. Okay. Any questions about this? Simple enough. After this, I'm going to summarize some properties about the logs. It's comparable to I summarized the properties for exponential functions, right? A summary. Okay. So maybe given a log function, a logarithmic function. Okay. The full name is logarithmic, so we just say a log function. So maybe f of x. In general, we say log to the base a of x. For any log function, there's a base. Okay. The base is a number, a constant. Okay. X is the variable. The same as exponential functions, it's always a good idea to specify the restriction of a. If you want to use the general case. Okay, now let's record the restriction on a. A is positive, right? A is not equal to 1. In short, it means a is a positive number, so not equal to 1, of course, right? And then we are going to summarize some properties. Okay. Actually, for all the log functions, as long as the function is defined, then the domain and the range are always the same. Okay. The domain of the function, you want to record the domain? I think we just did one particular one. For all the log functions, the domain is always the same. The domain of any log function is the set of all the positive numbers. Using the interval notation is the interval from 0 to infinity. So just try to remember the graph of the function we just did. Okay. And likewise, the range for any log function is the same as well. Okay. The range for any log function, using the particular log function we have seen earlier, the range of any log function is the set of all the real numbers. You just say all the real numbers. Using the interval notation, you denote the set of all the real numbers from using the interval notation as the open interval from negative infinity to infinity. Thirdly, there are two particular cases depending on the value of a. Okay. The same as before. A is positive number, so not equal to 1. So there are two cases when the base is in between 0 and 1. So the other case is when base is greater than 1. I will give two cases. If the base A is the base, okay. If the base A is greater than 1, it's a number like 1.2, 1.5, 10. And by the way, the log with the base of 10 is called common log. Common log. I think you did a lot of common log in high school. But in this course, you do not see common log too often. Okay. We mostly use natural log. Okay, if a value is 1, bigger than 1, I mean, if a value is greater than 1, then this function, the log function with the base of a is increasing. You just see a particular case, the natural log function. The natural log function is a log function with the base of e. E is 2.7 something. If you forgot, you can check on your calculator, which is greater than 1. The function is increasing, right? Likewise, if the base, again, there are only two cases, greater than 1 or in between 0 and 1. Okay, if the base is in between 0 and 1, I was trying to write then the function is decreasing. By increasing, we mean from left to right, from the left to the right, you are going uphill. By decreasing, we mean the graph of the function from the left to the right, you are going downhill. Okay. These are probably all the properties I want to summarize. Okay. Any questions about logs? I guess we are done logs. We are done logs now. Okay. If you don't have any questions, we'll move on to tricks. Okay. Actually, for trig functions, we are going to require 6 trig functions. Now you look at the list. Under item number 5, sine of x, cos of x, tan of x, cotan of x. Actually, 2 more on the next page, secant and cosecant. Okay. I know some people are scared of trigs, so don't worry. It's nothing hard. It's nothing hard. For trigs, I'm going to run a little bit slower. We'll use the unit circle later, okay, shortly. Before we talk about trigs in general, trigs is about an angle, right? We can compute sine value of an angle, cos value of an angle, tan value of an angle, and so on, right? In this course, you just remember, for the angle measurement, we never use degree. We never use degree measurement. Of course, you can use degree to think how large an angle is. We always use radian measurement. I want to repeat, we always use radian measurement. Okay. By that we mean, in many cases, you need to switch the mode of your calculator to radian mode. In many cases, you don't have to do that now. Okay. Of course, the first thing we need to do is to know the conversion between two measurements, the two ways to measure an angle. Okay. So maybe a relation between degree measurement, degree and radian. I mean. measurements. Actually, to do the conversion, there's only one formula you need to memorize. There's only one formula, one relation you need to memorize. You just remember pi radian. Using the one formula, you can do any conversion between degrees and the radians. Okay. The conversion is, you just remember one thing: pi radian. Pi radians. Pi is the pi you have been so familiar with, 3.14 something. It's a non-repeating irrational number. It's a non-repeating infinite decimal. It's an irrational number. Okay. You have pi button on your calculator. You do not have to check it. You know pi. You have seen pi over and over again. So this is the same pi. Okay. The only conversion you need to remember is pi radians is equal to 180 degrees. Now you look at the mouse cursor. The degree measurement, you just write a little circle in here. It means 180 degrees. Right. Again, pi radians is 180 degrees. In terms of angle, 180 degrees is a straight angle, right? An angle like this. Yeah, probably you want to imagine an angle always has an initial side, has a terminal side. Okay, so now let's say in rectangular coordinate system, you always put initial side in the same direction as the horizontal axis. Okay, now let's say the initial side of an angle is that side, and then the terminal side is this. Okay, and if you rotate an angle counterclockwise, then the measurement is positive. In terms of degree, if you have something like that, okay, initial side, now you look at the cursor, you look at the mouse cursor, the initial side is here, and then you rotate the angle counterclockwise. This angle, I was trying to say, this angle in terms of degrees is 90 degrees. So later on, so we're going to do conversion. Okay, now I'm trying to tell you how large 180 degrees is. Okay, and then you keep on going. The straight angle is an angle something like that, right? That's 180 degrees. In terms of radian, that's using the radian measurement. I mean, using the radian measurement, that's pi radian. Okay, that's pi radian. And then using this one, I told you earlier, we can do any conversion between degrees and radians. Okay. Now, for instance, how do you want to represent 1 degree in terms of radian? 1 degree, I think you used to have some tool called protractor. You can imagine how large 1 degree is, or at least you can imagine how large 90 degrees is, right? And then you can imagine 1 degree is very tiny. Okay. If you want to represent 1 degree to radian, you divide two sides of the equation by 180. The right hand side you see 1 degree, right? So 1 degree is equal to pi over 180 radian. And likewise, if you want to convert 1 radian, if you want to represent 1 radian in terms of how many degrees, in terms of degree measurements, so you can do this. Again, you look at the top equation. Okay, you divide two sides of the equation by pi. On the left hand side, you are going to have 1 radian. Okay. I was trying to say, I don't know what I was trying to write. I was trying to say 1 radian. If you want to convert 1 radian to degrees you divide two sides of the equation by pi. So 1 radian is equal to 180 over pi. That many degrees. You can imagine approximate value actually. Okay, 180 divided by pi. So maybe just use pi button on your calculator, or you can use approximate value of pi, 3.14 or something. Approximate value of pi is 3.14. That's as far as I can remember. Some people challenge their memory by memorizing the value of pi to how many decimal places, which is weird to me. But you just need to know pi is approximate value of pi, and pi is an irrational number. By that we mean it's a infinite non-repeating decimal. Okay. Actually, using this tool, you can do any conversion. Again, okay, the basic stuff is pi radians is equal to 180 degrees. Now let's try to represent some commonly used angles in terms of radians. Okay, now let's do some conversions. Okay, so now let's say if I want you to convert, so now let's say 60 degrees. Okay, now let's do some easier ones. Okay, if I want you to convert, so now let's say 90 degrees, represent 90 degrees in terms of a radian. You look at the equation again. From the right hand side, you divide two sides of the equation. From this equation, you divide two sides of the equation by 2. The right hand side, you are going to see 90 degrees, right? And then the left hand side, you are going to see half pi. Again, divide that equation by 2. You are going to have, you can represent 90 degrees in terms of radians. Okay, so that's half pi. Okay. Alternatively, you can use the second formula, the second relation. You multiply two sides of the equation by 90. You have 90 degrees, right? And then you also have the same thing, pi over 2, right? Again, to do any conversion, you just remember one formula, and then you can handle anything. Okay, some commonly used angle measurements. Now let's do one more. Okay, now let's do a few more. Actually, we need a few more. Okay, so now let's do one thing the other way around. Okay, now let's convert pi over 6 to degrees. And by the way, if you do not write the little circle, I do not always have to write radian, RAD. If you do not write anything for a angle, it means the radian measurements. So by that we mean pi over 6. I do not have to write radians. It means pi over 6 radians. Okay. Anybody want to tell me how to convert pi over 6 to degree measurements? How many degrees? Pi over 6. A simple way is you just replace pi with 180, or you go from here. Yeah, it's 30 degrees. Okay. 30 is coming from pi is equivalent to 180 degrees, right? You replace pi with 180. It's going to be a degree measurement. Okay. And then you divide 180 by 6. You have 30 degrees. After the conversion, you have to write a little circle for degree measurements. Okay, now let's. I believe now we can convert 45 degrees. Another commonly used angle. Okay, 45 degrees. You can look at this. You can go from here. You divide two sides of the equation of that by 2, you have 45 degrees on the left hand side. It's pi over 4 in radian. Okay. Or from the original relation, you divide two sides of the equation by 4, right? You have the same thing. Or from here, you multiply two sides of the equation by 45. You also have the same thing. Okay. Again, the very basic one to do any conversion is the first formula. Okay. I think we just need one more commonly used angle. Pi over 3. I think pi over 3. Now let's do the conversion from radian side to degree side. Pi over 3. Anybody want to write how many degrees? Pi over 3 radians is equivalent to how many degrees? 60. 60 is right. Okay. And then we can talk about the trig values. Actually, for an angle, we can also talk about an angle like 150 degrees. So now let's say something like 5 pi over 6 radians. Again, in rectangular coordinate system, in Cartesian coordinate system, I said the same thing twice. We always consider the positive direction of the horizontal axis is the initial side. The origin is here. Okay, the origin is always considered as the vertex of any angle. Okay, and then if you rotate initial side counterclockwise, then you have a positive angle. If you rotate the initial side clockwise, then you have negative angle. Okay, so now let's say this angle in terms of radian is half pi. Get used to radian measurements. Okay, half pi. Initial side is the positive direction of x-axis. I'm trying to say if you rotate the initial side that way by 90 degrees by half pi, this angle would be considered as negative pi over 2. So negative half pi or negative 90 degrees. Okay. You can also talk about, so now let's say 230 degrees. So what's 230? Now let's I was trying to say 360 degrees. I was trying to say 360. Okay. How large is 360 degrees? A complete rotation, right? Is 360 degrees. So that makes sense. Actually, we can also talk about 720 degrees. 720 degrees, you start from here, you rotate twice. You have 720 degrees. Okay. I'm trying to say in rectangular coordinate system, we can talk about any angle measurements. The angle can be any real number. The angle can be 180, so it can be 360, can be negative 180. How do you describe negative 180 degrees? Negative 180, you would rotate the initial side around the origin. So did I say negative 180 degrees? Negative 180 degrees, you rotate initial side around the origin clockwise by 180 degrees. This angle is negative 180 degrees. Okay. Which is the same thing as in terms of radian measurements. It's negative pi radians. You do not have to say radians. You do not have to write radians. Okay. So did I make the angle thing clear? After you know the angles, now for the angles we can talk about any angle. Okay. In particular, we can talk about the trig values of any angle. We can talk about sine values of any angle, cos value of any angle, tan value of any angle, cotangent value of any angle, secant and cosecant value of any angle. Okay. Again, we require 6 trig functions. After you know the meaning of the degrees, we're ready to define trig values. For this thing, I do not want to run too fast. Okay. Probably you can recall a slogan you have been learning a few times in high school. Probably started from the junior high school. Sokatowating. Okay. Sokatowating. I was trying to write definition. Well, we start from the SOHCAHTOA thing. Okay. In a right triangle, I'm going to call this angle. Actually, the commonly used notation for angles is theta. Okay, just call this angle theta. Theta. Okay, I said theta. A Greek letter using that notation. Again, the setup is in a right triangle. By right triangle, I mean one angle has 90 degrees. The measurement of one angle is 90 degrees. Okay. Relative to angle theta. Now I want you to recall some terms. Relative to angle theta. So do you want to tell me how to call this leg? How to call this leg? Okay, I'm going to label some letters. I will call that point A. I'm going to call that point B. I'm going to call that point C. Relative to angle theta, how do you want to tell me, how do we call AC? A little reminder in terms of opposite adjacent hypotenuse. Relative to angle theta, how do you call AC? How do you call that leg? It's opposite, right? It's opposite. Okay. I'm going to use OPP to denote the opposite. Okay. Relative to angle B, that's opposite side. Okay. And the BC relative to angle theta, BC is called adjacent. I'm going to use ADJ to denote adjacent. And the longest leg in a right triangle, I mean the side opposite to the right angle is the longest, of course, right? So this one is hypotenuse, right? Hypotenuse. You can remember the term, right? After you know this, and then we can use these terms to define the trig values, all 6 trig values of angle theta in the special case. Okay, now the definition. Okay, I'm going to, at this point, I guess you can recall the slogan you learned in high school, the SOHCAHTOA thing. Okay. I'm not too familiar with the SOHCAHTOA thing. Okay, now we are going to define sine of theta. Sine of theta is defined as opposite over hypotenuse, right? I will give the definition in terms of opposite adjacent hypotenuse first. Sine of theta is opposite over hypotenuse. If you can recall it on your own, it's better. So you don't have to memorize too many things. Anybody want to tell me how we define cos of theta in terms of opposite hypotenuse and adjacent and stuff? Yeah, that's right. Adjacent over hypotenuse. And then tan of theta, you learned this from before. Tan of theta is opposite over adjacent. I think that's kind of SOHCAHTOA. I will try to. You see, now you follow the mouse cursor. Okay. You have sine is defined as opposite over hypotenuse. You have right, and then you have ka, you have to. Wow, I don't know where wa is. It's okay. I think you got the idea. And then three more you need to remember. Okay, and then cotangent of theta. Cotangent of theta is defined as two is to remember that cotangent is kind of reciprocal of tan. So which is defined that from tan, you switch the numerator and the denominator. You have cotangent. Okay, you have the definition of cotangent. So which by that we mean you have adjacent on top, right? Over opposite. I will write it both ways. Maybe it's actually 1 over tan of theta. Okay. Two more. Secant of theta is equal to. You want to remember 1 over cos first. From cos, you invert the numerator and the denominator. You have you have hypotenuse on top, right? Adjacent at the bottom. One more, cosecant of theta. Okay, is equal to 1 over sine of theta. So which is hypotenuse on top and opposite on denominator. Alright, so that's a simple definition how the trig values are defined. However, this definition applies only to the case when theta is one of the angles in a right triangle. By that we mean there's a restriction on theta. In this case, in this definition, theta can only be defined when an angle is greater than 0 and less than 90 degrees, right? In a right triangle, now let's recall in a right triangle, an angle cannot be more than 90. So does that make sense? Now I'm going to generalize the definition to any angle. I wanted to mention the SOHCAHTOA thing, so because I want you to try to memorize the general definition. It's kind of coming from the SOHCAHTOA thing, but it's going to be more general. For any angle, it's possible to define the trig values, all the trig values of any angle. Okay. I will write the definition on the next screen. Okay. After this, we are going to compute some trig values. So don't worry, it's simple stuff. So maybe now let theta be any angle. Before we define the angle, probably I can write it here together. Okay. Before you get the trig values of any angle, you have to put the angle in standard position first. By the standard position, we mean the initial side of the angle is in the positive direction of horizontal axis. I will show the meaning very shortly. I told you before, the initial side is always the positive direction of x-axis. Okay. Now let theta be any angle in standard position. In the standard position. I told you the meaning. I'm not going to write the meaning. Okay. Again, you specify the direction of initial side of the angle. Okay. I will draw a picture to tell you the meaning. Okay. So can I say the angle is here? Actually, I will convince you soon. The definition applies to any angle very shortly. Okay. That's the angle theta. Okay. A angle has an initial side, has a terminal side. The initial side is always x line. Okay. Okay. To define the trig value, we need to choose a point on the terminal side. Okay. I will do it in 2 steps. Okay. You choose any point on terminal side. Choose a point on the terminal side. On the terminal side. I'm not going to try too many of those. Choose any point on the terminal side. Okay. Now let's say the x coordinate is x and the y coordinate is y. Any point on the terminal side, actually any point in the rectangular coordinate plane has 2 coordinates, right? X coordinate and y coordinate. You know that. Okay. So maybe say any point. Okay. The point with x coordinate of x and the y coordinate of y. Actually, so later on for some particular angles, I'm going to tell you what point to choose so that it's easier to compute the trig values. Choose a point on the terminal side. We need one other number. The other number is the distance between the origin and the point. Okay. So now let r be the distance between the origin O, the origin and the point xy. I believe it's not hard to compute using the Pythagorean. I'm going to write that in brackets. R value is actually always the same thing as square root of x squared and plus y squared. Right? So do you see a little triangle in here? That's x. That length is y, right? In this little red triangle, that's x, so that's y. The distance between the origin and the point is r. I think that's r. I'm going to label r as well. Okay. After getting the values of x, y, and r, and then we can define all the trig values in terms of x, y, and r. Now it should be simple. Okay. Now we are ready to define all the trig values. Now let's start with sine of theta. Sine of theta. Now do you want to recall it's defined in terms of SOHCAHTOA stuff as opposite over hypotenuse? In this little picture, you can see it's defined as y over r, right? And so likewise, cos of theta is x over r, right? You look at the triangle again, x value is adjacent relative to theta, r value is hypotenuse. and the tan of theta is defined as y over x, right? 3 more. Cosine of theta is defined as, you look at the tan, you invert the numerator and the denominator, you have the definition of cotan, so which is x over y, right? And 2 more. Okay, secant of theta, you look at cos, you invert the numerator and the denominator. In here you have r over x, I mean. Cosecant of theta is defined as r over y, of course. Okay. The definition is simple. I'm going to make more comments on why this definition is more general. The angle, according to the new definition, the angle is not necessarily an angle in between 0 and 90 degrees. The angle actually, it can be any angle. For any angle, you have a terminal point, right? You have a terminal side, I mean. And then you choose any point on terminal side. You have x value, you have y value, you have r value. And then you can define the trig values for any angle. That's why I said this definition is more general. So that makes sense? But essentially it's coming from the special case, the SOHCAHTOA stuff. Okay. Any questions about this? Yeah, probably you cannot fully understand that thing without doing more questions. Now we're going to do more questions. Okay. In most cases, we only you only need to be able to use the definition to get the trig values of some spatial angles. Actually, the key is how to choose the terminal a point on terminal side. Probably you have seen a picture like that before in high school. It's called the unit circle. The unit circle is very helpful to choose a point on terminal side. In the definition, you remember you can choose any point on terminal side. Now using the unit circle, you can it will help you to choose a point. Actually, you just choose a point on the unit circle, and then you have x value, you have y value, right? And then you can compute the trig values of any angle. Any angle falls in. Any angle can be located on the unit circle. So that makes sense? Okay, I will make my point using. Now we are going to do a few questions. I will use the unit circle. Okay. So don't worry. For any quiz, starting from assignment 2, for any assignment, for any midterm or the final or whatever thing, I'm going to include the unit circle on paper. Okay. Using the unit circle, we are going to do some questions. Probably I'm going to keep it a little bigger of this size. Okay. Okay, we start from a simple one. Okay. Now, for example, find all the trig values. By that we mean sine, cos, tan, cotan, secant, cosecant. Find all trig values of a angle theta. So now let's say theta equals. Now let's do a simple one first. Okay, so maybe pi over 4. Okay, now the solution. The first question I'm doing is I will put the angle in standard position. Okay, put the angle of theta pi over 4 in in the standard position. Now you look at the mouse cursor. Initial set is that, right? Positive direction of x-axis, and then you rotate initial set counterclockwise by 45 degrees by pi over 4. The degree equivalent for pi over 4 is 45 degrees. You see the two angles 45 degrees, pi over 4. You imagine the terminal set. Okay, I think I can draw something on that. So the terminal set is that. Illustration only. Okay, that is the terminal set. That's the angle in standard position. And then in general, you choose any point on terminal set. You choose any point on terminal set. So, but in order it's easier to compute the trig values, you always try to choose the point on the unit circle. And by the way, by unit circle we mean the radius of the circle is equal to 1. The radius of the circle is equal to 1. The circle is centered at the origin with the radius of 1. That's the unit circle in the diagram. Okay. The first thing you do is to put the angle in standard position. Okay. Can I write 3 steps? Yeah, probably it's easier to say that way. Okay. Secondly, we choose a point. Okay. So this time the point you want to choose is the point on the unit circle. So the point is the point with x coordinate of square root of 2 over 2 and the y coordinate of square root of 2 over 2, right? Choose the point of that on terminal set. So we have x value. X value is the x coordinate of the point, right? The square root of 2 over 2, and the y value is the y coordinate of the point, the same number, right? You have x value and the y value. Okay. Anybody want to tell me the r value? What is the value of r? R value is the distance between the origin and the point. I'm looking at the chat. Anybody want to tell me the value of r? It's a unit circle. The point is on the circle. The circle has radius of 1, right? R value is 1. So does that make sense? The circle is a unit circle centered at the origin with a radius of 1. All the points are on the circle. The distance between the point and the origin is always 1. Okay. That's one good thing about using the unit circle. Now you have x value, you have y value, you have r value. Okay. Lastly, you can get all the trig values of the angle pi over 4. Okay. So by that we mean, so now let's say tan of pi over 4. Why do I do tan first? Now we do sine or cos first. Okay. Now concentrate when we do this question, I will tell you some tricks. Okay. Sine of pi over 4. Now this time the angle is pi over 4. Sine of pi over 4 is y over r, right? I'm going to write the formula for this particular case. It's y over r. Y over r is equal to, I did something wrong here. Square root of 2 over 2. R value is 1, okay? Y value is square root of 2 over 2. You just write sine value is that, okay? So do you see something in general? Actually, y coordinate of the point is always the sine value, okay? So do you see y coordinate of this point is always sine value? We'll do some others very quickly. Now you listen to my questions. Try to write your answer in the chat. So tell me sine of pi over 6. Sine of pi over 6. You look at the cursor. You look at the cursor. I'm looking for sine of pi over 6. Anybody want to tell me sine of pi over 6 using the trick I just told you? Y coordinate of the point on unit circle is always sine value of the angle. So please, anybody want to write sine value of pi over 6? Sine of, yeah, that's 1/2. And likewise, sine of pi over 3 is square root of 3 over 2. I'm trying to say using the unit circle, it's easy to identify sine value of any angle. You just look at the y coordinate of the point. That's sine value of any angle. Okay, so maybe sine of 90 degrees, sine of 90 degrees, sine of half pi. Sine of half pi, please. It's 1. Okay, that's a common sine value of angle. Okay, sine of 90 degrees, sine of half pi is equal to 1. You look at the y coordinate. Okay, actually from the question I was talking about something in general. Okay, so likewise we can compute the cos value of pi over 4. Now let's recall cos value is defined in terms of x, y, and r as x over r, right? We have x value, we have r value, we have y value, and so on. So this time r value is the same thing as 1. R value is 1. Okay, you just look at x coordinate. X value is square root of 2 over 2. Okay. By that we mean, now you look at the mouse cursor. X coordinate of the point on the unit circle gives you the cos value of the angle. You got me? I'll check if you got it. Okay. So do you want to tell me cos of now let's say pi over 3? Cos of pi over 3, please. Cos of pi over 3. Cos of pi over 3, please. I'm looking at the chat. Yeah, 1/2 again, right? Cos of pi over 6 is square root of 3 over 2. And I will look for one more. Okay. Cos of 2 pi over 3. What is cos of 2 pi over 3? Cos of 2 pi over 3, please. Cos of 2 pi over 3 is negative 1/2. Right, easy. You just look at the point and look at x coordinate. That's the cos value of the angle. Okay. Tan value is a little bit more complicated. You need to do a little bit more work. You need to use the definition of tan. Tan is defined as y over x, right? In this particular case, it's easy. X value and the y value is the same for this angle. So tan of pi over 4 is 1. Probably you can remember that's a famous tan value. Okay, tan of pi over 4 is 1. Tan of 45 degrees is 1, right? for any angle you need to divide. Okay, for this one I will do this one in some more detail. Tan of pi over 4 is defined as y over x, right? Y over x. X value and y value is equal. Yeah, that's why tan of pi over 4 is equal to 1. Okay. To get the tan value for any angle, you need to divide x coordinate into y coordinate. Okay. Right. And of course, cotan value, you just invert the numerator and the denominator from tan value. This one is 1 as well. Okay. And the secant value, secant of pi over 4 is equal to, now you look at cos. You invert the numerator and the denominator from here. I think you have square root of 2 over square root of 2. This number is kind of weird, but it doesn't matter. You just write this way, it's fine. Okay. It's 2 over square root of 2. Actually, yeah, probably you can remember how to simplify that. Okay, the numerator, it can be written as, I will write a long version. Okay, can be written as square root of 2, the whole thing squared. The denominator is square root of 2, and then you cancel out 1 square root of 2. You have the answer of square root of 2. Actually, it doesn't matter. Either way is okay. I'm trying to say either that way or that way is okay. And by the way, it's calculus. In many cases, I want this form. This form is better than using calculator to convert the number to 1.414 something. Okay, I'm trying to say when you have a radical something like this, you can leave the radical as the final answer. And likewise, cosecant of pi over 4. I think the same thing, right? It's also square root of 2. That's a simple question designed to illustrate how to get all the trig values using the unit circle. Again, sine value and cos value are easy to identify if you know a point on the unit circle. And the tan value, you need to do a little bit more work. You need to divide x coordinate into y coordinate, right? After getting sine, cos, and tan, and then it's easy to identify cotan, secant, and cosecant value of the angle. We'll compute the trig values of one more angle. So this time we'll do a weird angle. Now let's do pi. Okay. Another question is, now for example, find all trig values of pi. For this one, I'm going to run a little bit faster. I think you got the idea. I do not write the wording. Okay. You locate pi. Pi is equivalent to 180 degrees. The terminal side of angle pi is here. So the angle, you rotate the angle clockwise, you have a positive angle. You have the angle pi. Okay. Now we are going to get all trig values of pi. So maybe you could tell me the answers. Okay, I'm looking at the chat. Okay, you try a little while. Okay, I'm looking for sine of pi. I'm looking for cos of pi. I'm looking for tan of pi. So this time I want you to try this one on your own. Okay, and then we compare the answers. Of course, I'm looking for cotan of pi. I'm looking for secant of pi. I'm looking for cosecant of pi. If you want, we can also do it together. So tell me the answer to sine of pi. You look at this point. And then y, you remember I told you y coordinate of the point gives you sine value of the angle. Sine of pi, please. Sine of pi. You look at the cursor, okay? Sine of pi, please. 0. 0 is right. Cos of pi, please. Cos of pi. Cos of pi, please. -1. And then tan of pi. Y coordinate divided by x coordinate. Tan of pi, please. Tan is defined as y over x, right? Y over x. Tan of pi, please. Tan of pi. The answer, I'm looking for the answer. It's computed using 0 over -1. The answer is 0, right? A fraction is a division, it's 0. Okay. And then cosine of pi, please. A little tricky. Cosine of pi. Cosine of pi, please. Cosine of pi is defined as x over y. Okay. X over y. Undefined is right. 0, whenever you see 0 on denominator, is undefined. Okay. So cosine of pi is undefined. Secant of pi, please. Secant of pi. Secant of pi is defined as in terms of x, y, and r. It's defined as r over x. R value is always 1. Anybody want to tell me secant of pi? Secant of pi? Or you can remember the relation between, yes, -1. Or you can use the relation between secant and cos. Okay. Secant of pi is the same thing as 1 over cos of pi. You see it's -1. Cosecant of pi is r over y. Cosecant of pi, please. Undefined, right? Now the bottom line. In the future, if I give you the unit circle, I want you to be able to identify all the trig values of some common angles right away. Okay. Now, for instance, you just look at y coordinate, you have the sine value. You look at the x coordinate, you have cos value, right? You divide two numbers, you have tan value, and then you use the relation between cota and tan, the relation between secant and cos, the relation between cosecant and sine. You can have all other trig values. So does that make sense? Okay. Yeah, probably these two questions are sufficient for you to be able to identify all the trig values, right? Any questions about this? Now you know how to identify all the trig values. Okay. And then we're ready to talk about all the trig functions. We're going to talk about sine function, cos function, tan function, cotan function, using some trig values. Okay. Probably we can still use we can still look at the unit circle. I will do at least one of them in some details. and then I will leave others for your as assignment questions. Okay, now you look at that. So in this question, we concentrate on sine of x. Okay, we are trying to answer 4 questions. So maybe the solution. For this one, we evaluate the function at different numbers. Okay, and then we get the domain of the function. We get the graph of the function. We get the range of the function, and so on. Okay, we'll go over the list very quickly. Okay, the value of the function at 0 is equal to 0. You look at sine of 0. The angle of 0 is here. You look at the x coordinate. I believe you will see sine of 0 is equal to 0. The value of the function at 0 is 0. Sine of 0 is 0. Super common sine value. Probably you want to memorize that actually. And then the value of the function at pi over 6. You look at the angle pi over 6. I think sine value of pi over 6 is 1/2, right? And then we make the angle a little bigger. The value of the function at pi over 3. We're trying to get sine value of pi over 3. You know it's, you look at y coordinate. I think I missed one, but it's okay. Square root of 3 over 2. Square root of 3 over 2. I'm going back to the value of the function at pi over 4. We are trying to compute sine of pi over 4. I think you have you look at the mouse cursor, y coordinate of that point, square root of 2 over 2. Some people use the form, so now let's say 1 over square root of 2. Actually the same thing. Okay. Either form is okay with me. And then the value of the function at half pi, right? Sine of half pi, so which is 1. Another commonly used angle. So this time I will do 2 more, and then you tell me 2 more. Okay, I will do 2 more. Okay. So how about we do a weird angle? The value of the function at so now let's say now let's do a weird one. Okay, so now let's say NumPy so give me a little moment. Okay. Okay, we'll do a weird one. 13 pi over 6. 13 pi over 6. I'm trying to say the function is defined actually at any real number. 13 pi over 6. 13 pi over 6 is kind of, so that's my scratch paper, okay? 13 pi over 6 is kind of 2 pi and then plus pi over 6. If you do a little fraction addition, you can see that. So what's the angle of 2 pi? The angle of 2 pi is, that's 1 pi, right? You rotate the initial point of the angle counterclockwise by a complete rotation, that's 2 pi. And then you add another pi over 6. So do you see the terminal point of 13 pi over 6 is actually here? Now tell me the value of the angle, please. Sine value of 13 pi over 6. So please, after a complete rotation, you add pi over 6. So the terminal side of the angle is the same thing as pi over 6. So that makes sense? It's 1/2, right? I'm trying to say we can evaluate sine value of the angle at any number. So not only in between 0 and 2 pi. You can do more than one rotation. You can even rotate the angle anyway. Okay. So clockwise, you can have negative angles. Okay. Now let's do one more. Okay. The value of the function. So maybe at negative pi over 4. At negative pi over 4, please. I'm not giving you any hint. So tell me the sine value of negative pi over 4, please. Write your answer in the chat. If you have trouble, I'm going to give you some hint. Initial side is here. Pi over 4 is is equivalent to 45 degrees. You rotate the initial side clockwise by 45 degrees. So do you see you have the terminal side in here? Yeah, the terminal side is the same thing as the terminal side of 7 pi over 4. So which means the sine value. I know it's hard for you guys to write square root stuff in the chat, but you look at, I'm trying to say, you look at y coordinate of this part, you have the sine value of the angle. Okay, it's a negative square root of 2 over 2, right? So that makes sense. I just want you to see the function is defined at any real number, right? At any number, at 0, at any positive number, represented by this, at any negative number, represented by this, right? Now we are ready to get the domain of the function. Okay. Anybody want to tell me the domain of the function, please? The domain of the function, please? The domain of the function? I just said it's defined at any real number. It's using the interval notation. It's the open interval from negative infinity to infinity. It means we can evaluate sine function at any real number, right? It means every real number is in the domain. It means the function is defined at any real number. The same thing. So we have the domain. Okay. Now we are ready to get the graph. So this time, to get the graph, you do not use the unit circle. You treat 0, pi over 6, these guys as x values. So by that we mean, now for the setup, x coordinate is going to be the measurement of the angles. And then again, each value of the function determines a point on the graph. Now for instance, the value of the function at 0 is equal to 0. It means the origin is on the graph. Now let's say the value of the function at half pi, so equals 1. So now let's say half pi is here. Pi is 3.14. Half pi, I believe you can imagine what's half pi. Okay. The value of the function at half pi is equal to 1. So now let's say 1 is here. This point is on the graph. I'm trying to say the point with x coordinate of 0, y coordinate of 0 is on the graph. The point with x coordinate of, you look at that value, okay? The point with x coordinate of half pi and y coordinate of 1 is on the graph. You have many inputs, and then many inputs will determine many points on the graph. Okay, and then you connect many points. I believe you can remember the graph. You learned the graph in high school. I just help you to record the details. Okay, so the graph of sine is something like that. It's oscillating in between -1 and 1. I'm going to show you the computer sketch. Then I'm going to make some comments. I will try to check if they need. You see, even in this, they don't need the brackets. For sine of x, the convention is you do not need to use brackets. It's okay to use brackets. I will zoom in a little bit. You see, the origin is on the graph, right? The origin is on the graph. So what's that point? On the screen it shows it's half pi 1, right? The point with the x coordinate of half pi and the y coordinate of 1. I like this graphing stuff. Half pi is a pi is 3.14 something. Half pi is half of 3.14. I think it's 1.5 something. 1.5 something. It's here, right? Probably I said it wrong. Okay. Anyway, the point with the x coordinate of half pi and the y coordinate of pi is on the graph. I'm pretty sure it's going to show this point, pi 0. Okay. Some other special points. So now let's say when x coordinate is, you just go through this. Okay. So this one is the computer sketch. It's oscillating in between 0 and 1. You see the domain is the set of all the real numbers from -infinity to infinity. But for the graph, I'm going to tell you a better way to write the graph. In most cases, it's easier to label the horizontal axis using multiples of pi. By that we mean I will try to make this as good as possible. Okay. You label the horizontal axis using multiples of pi. Probably you want to half pi is here. Now let's say pi is here, right? On this side you have negative half pi in here. You kind of have negative pi in here. Okay. So of course everything is in multiples of pi on the horizontal axis. Okay. The origins here. You have 1 in here. You have -1 in here. Illustration only. Okay. I just sketch the graph when x is in between negative pi and the pi. The origin is on the curve, right? You have this point on the graph, and then you have the value of the function at half pi is equal to 1. You have this point, and you have this point. Okay. On this side, of course, you have this point. The value of the function at negative half pi is equal to -1. You can kind of see it from here, from the unit circle. Okay, it's something like this. That is the graph in between negative half pi, in between negative pi and the pi. Of course, it goes forever in both directions. I really hope some computer sketch can give you something like this, or graphing calculator could give you something like this. It's easier to see many properties. Okay. Try to memorize the graph. The graph is very useful later in the course. For instance, after you memorize the graph, you see sine of negative half pi is equal to -1. sine of 0 is 0, sine of half pi is 1, sine of pi is 0, and so on. Okay. Try to memorize the graphs of many commonly used functions. Okay. It's going to be useful for many purposes. Alright, so we did the graph. Lastly, we're looking for the range of the function, please. The range. Anybody want to tell me the range, please? The range. After getting the graph, you see the range. Yeah, the closed interval in between -1 and 1. So that is the range. Okay. You see the y values on the graph, y coordinates on the graph, or the graph is oscillating in between -1 and 1. -1 and 1 are included in the range. So we have the graph of sine of x, right? Any questions about this? For the trig functions, we require the graphs of sine, cos, tan, and cotan. Okay. For other trig functions, I'm going to go over a little bit quicker. I think you got the idea already. For cos of x, I'm not going to evaluate the function. You know how to evaluate anyway. We mentioned how to evaluate cos already, right? I just show you the graph, and then we'll make some comments on the graph. We go from there. Anyway, I will show you the computer sketch first, and then I will show you a better sketch labeled the horizontal axis using multiples of pi. Okay. I will show you the computer sketch first. Now we're talking about cos of x. The graph is something like that. If you label using multiples of pi, this point has x coordinate of half pi, right? This point has x coordinate of pi. You see some super important points on the graph. I think I really like this thing. Okay. Right. Then I will show you a better way to sketch the graph of cos. Okay. Better way, or not better way. I mean, I'm trying to label the horizontal axis using multiples of pi. Origins here, so now let's say half pi is here. Now let's say pi is here. I still draw the graph, sketch the graph in between -pi and pi. So now let's say negative half pi is here, and then you have negative pi in here. You remember cos of 0 is equal to, you look at the angle of 0, okay? Cos of 0 is equal to 1, right? Cos of 0 is 1. So you have a point. Now let's say 1 is here. That is a point on the graph. That is a point on the graph. Okay. If you look at the unit circle, you have cos of half pi is equal to 0. Cos of half pi is equal to 0. So this point is on the graph. Likewise, this point is on the graph. Okay. Cos of pi is -1. Say -1 is here. So this point is on the graph. This point is on the graph. So the graph is kind of that, in between negative pi and pi. I just redid the graph. It's not too nice looking, but I was trying to show you some important points on the graph. Again, the computer sketch is something like this. In between negative half pi and half pi, I just sketch the graph from here to here. Yeah, that's good. I can do dots on the graph. Actually, for cos, we can also talk about the domain and the range. You see the domain, the cos function is defined at all the real numbers, right? So like sine, the range is in between -1 and 1. For this function, I just did not do the values, okay? But it's easy for you guys to compute the values. That's cos. So questions? Any questions about cos? If you don't have any questions, we'll move on to tan. Okay, tan is a little bit weird. The next question is the function is tan of x. Again, we only talk about the domain, range, and the graph. I've never seen hot decimal sketch tan. I hope that's something I want. That's okay. Tan something like this. Tan something like this. I will show you a better way to understand tan. Okay, so don't worry. So this point is positive half pi. This point is positive half pi in between two branches. The middle between two branches. So can I say that way? It's not too precise, but in between these two branches, at this location you have a vertical asymptote. This location is when x value is half pi. I will show you my sketch. You will know what I mean. Again, you label something like half pi in here, so maybe a pi in here, negative half pi in here. Actually, for this one, I do not want to include pi. I will remove that pi. You will know what I mean very shortly. Okay. So first of all, I'm going to sketch the branch in between negative half pi and half pi. Okay. To sketch, you draw two vertical asymptotes. I told you there are some vertical asymptotes, right? You use the dotted line to denote this line is not on the curve. The dotted lines are vertical asymptotes. Okay. When tan is in between negative half pi and half pi, this branch is kind of like that. You see two vertical asymptotes. If you want to compare with the computer sketch, I was trying to draw the center branch. Can I say center? It's not precise either. I was trying to draw that branch, the center branch, on the screen. Okay. Of course, it has many other branches. The branch to the right, the next one is in between half pi. I believe this point is pi, and then you need one more point. This point is 3 pi over 2. You add another half pi. Okay. The next branch is in between half pi and 3 pi over 2. At this location, you have a vertical asymptote. You have another branch. Illustration only. Okay. On this side, you also have so now let's say negative pi, negative 3 pi over 2. Okay. At this location, you have another vertical asymptote. You have another branch, something like this. Of course, it has many branches. You can go forever to the right, forever to the left. Okay. That is the graph. Okay. On the assignment, I'm going to ask you to do more work to evaluate, but I want to tell you how to get the domain of the function. How can we write the domain of the function? So first of all, you identify at what numbers the function is undefined. I want to repeat. First of all, you identify at what numbers the function is undefined. You see the function is undefined at negative half pi, at half pi, at wherever you see vertical asymptotes, right? And then, okay, I will tell you how to write the domain. It's going to be a question on your assignment anyway. Okay. The function is defined at an open interval from negative half pi to half pi, right? And then you write the next interval using the union notation. Union. I know in high school textbook you are told to do something a little bit more weird, using some k, but you do not have to write that way. Okay. Union. The next interval is from half pi to 3 pi over 2, right? Probably it's better to write another interval from negative 3 pi over 2 to negative half pi. And then you just use dot notation. I will show you what I mean. Dot notation. Dot notation to indicate there are many other open intervals. Okay. I believe you have seen the pattern. As long as you can see the pattern, it's fine. Okay. You just write the domain that way, right? The range should be simple. Okay. The range should be simple. So anybody want to tell me the range? The range is the set of all the real numbers. You see the y values on the curve can take any real number, right? Yeah, that's right. Cool. I will make a little bit of comment on cotangent. Okay. If the function is cotangent of x, again, I will show you the computer sketch. I will show you my sketch. cosine of x is something like that. You look at one branch. One branch is in between 0 and pi. Okay. I will show you one branch. I will show you two branches. It also has vertical asymptotes. The vertical axis is one of the vertical asymptotes. Okay. So the graph is something like that, decreasing one branch. The branch after that is something like this. You got the idea? You see the shape? Okay. The domain, the origin is here. You see the origin is in the domain. No, the origin is not in the domain. I mean, the interval from 0 to pi is in the domain. Okay. And to the right of that, you have from pi to 2 pi. I believe you can see the pattern. Union forever. On this side, you have the open interval from negative pi to 0, right? I think you know what I mean already. And then union forever. I still have 1 minute to talk about the range. You see the range. You see the range is the same thing as tan, from negative infinity to infinity. Okay, I told you the domain. I told you the range. I told you how to evaluate the function.